Hey everybody, welcome to Lecture 8 of Environmental Science 347 Climatology. Moving now into the heart of the mid part of the course. We're talking about climate and air-sea interactions. So this is probably the most oceanographic lecture of the entire course. We've talked so much about the atmosphere up to this time, but now we want to talk about how the atmosphere and the oceans are coupled, how those interactions ultimately drive climate on land. So how do these interactions between the air, the atmosphere, and the oceans impact global climate and the short-term climate variability of any one particular area? First, let's talk about how the water is moving around in the oceans. And this is called Ekman transport, basically blowing water around. Intuitively, you think, well, the water blows, so it's dragging the water, the air blows, so it's dragging the water along. And that's right to an extent. However, it isn't perfect. I'll get to why in just a minute. So probably and intuitively, we kind of get the idea that the oceans influence the heating and cooling of the planet, as the primary control of solar radiation is absorbed at the Earth's surface. The planet's mostly water, about 3/4. So when we think about radiation that's getting down to the ground level, or in this case, the ocean level, more than half of the planet's covered by water. So that when we look at the planetary balance of energy, that's one of the things that really drives it. It also contributes to heat fluxes from the ocean to the air and the other way around, both latent heat and sensible heat. Remember, when we talk about latent heat fluxes, this has to do with evaporation and condensation, moving your water from one phase to the other. So, of course, on top of the water and the air, you've got all this molecules going back and forth between the interface, between the air and the liquid, or sometimes the ice. That's going to be a latent heat flux. And then there are the sensible heat fluxes, which are more in line with convection and to a much lesser extent conduction. There's really not that much true conduction. It's mostly convective currents over top of the ocean. So when we think about how the energy or heat energy is moving around, all right, when we think about the ocean and we think about the atmosphere being so tightly coupled in these wind-driven currents, all right, the biggest one for our part of the world, the eastern part of North America, is the Gulf Stream. That's where there is very warm water coming up from the tropics, kind of hugging the southeast coast of the United States, moving north and northeast, and then peeling off and going into the open waters of the North Atlantic. But there are lots of ocean currents that are moving warm water, that are moving cool water in all different places across the globe. In fact, counter to what we have here on the East Coast, the West Coast has a California current, and that one is coming from north to south, which was part of the reason that the ocean water off the California coast is almost always colder than the water off the southeast coast of the United States. The waters off the southeast coast of the U.S. have their origins in the tropics, whereas the waters off the California coast have their origins in the Gulf of Alaska. So the origins of that water mean a lot. Back to that Ekman transport term. So this is the foundation of moving subsurface water, the water that's not immediately at the top of the ocean surface. Remember that the ocean in some places is miles deep, right? So this is a simplified model of how the water is moving when you look at the air that is stressed over top of the water. So the wind blows on the water or blows over top of the water, it induces a stress or pulling on the water, but it doesn't necessarily pull it in the same way as the air is moving. Because why? Well, because the planet is turning, remember? So there's going to be a little bit of a turning of a fluid, and that's what we see here in the Ekman spiral. Basically, what the Ekman spiral says is the farther you go down in the water, the more the direction of that water is turning. All right, so at the surface layer, if your wind is blowing to the north, let's say at 0 degrees, think about the compass, 0 to 180, 270 and around like that. If your wind is blowing north, your water right beneath that wind is actually going to be going toward the northeast. So it curves about 45 degrees from the direction of the wind. And then in the layer below that, it angles another 45 degrees. And then as you go deeper and deeper and deeper, that curl continues, but the strength of motion, in other words, how fast that motion is going, decreases dramatically because you're away from your wind now. So that thing that's driving the ocean current, you're gotten too deep. All right, so most of your motion of the ocean, if you will, is going to be in that top several hundred yards or meters of the ocean. All right, so Ekman transport basically tells us with that spiral that the motion of the water is going to be curled around clockwise as you go down in depth, with respect to direction of the wind. Because of this, the ocean is not exactly the same height everywhere, which is kind of weird to think about, but the ocean isn't the same height everywhere. This tends to pile up waters and makes it a little bit higher than in some places than others. I mean, not like dozens and dozens and dozens of feet. And a lot of places it's just a few inches or a few centimeters. All right, but this does actually lead to a net piling up of water. And in turn, that is what affects ocean currents. Between the Ekman transport, the fact that the Earth is turning, that ends up affecting ocean currents. So the ocean's a fluid just like the air is, so it flows. And it is still on a rotating surface, the Earth, so it flows. So it is subject to the Coriolis effect. All right, remember the Coriolis effect, that is almost zero close to the equator, and maximized, that spin is almost maximized right at the poles, whether that's the North Pole or the South Pole. All right, so that curvature to the right, if you will, almost nothing right at the equator, but then as your latitude goes either toward the North or South Pole, that curvature, as something flows away from the equator, is turning more toward the right, southern hemisphere to the left. All right. And again, that's the geostrophic flow, that balance, just like it is in the atmosphere between a gradient and a Coriolis. So with the Ekman transport and fluid subsurface tending to turn to the right, you end up with small maximums, if you will, or maxima in ocean height in the middle of a big ocean basin. So let's think about just the North Atlantic Ocean. North of the equator, east of the North America, west of Europe, it's a big ocean basin, all right? So in the middle of that, the ocean is actually a little bit taller or a little higher, all right? So we call that a gyre. That spinning around that area is a gyre, all right? The Ekman transport causes that water to converge near that center, okay? But because of gravity and the Coriolis effect, the current around there isn't perfectly geostrophic. It actually bends out a little bit from that center of circulation. Think of that little bulge in the water like an area of high pressure in the atmosphere. All right. The flow is out and clockwise from that. So it's not perfectly clockwise, but it's slightly outward from the center and clockwise. So that talks about moving the water laterally or horizontally, okay? But sooner or later, the water bumps into stuff, continents, right? And at that point, some of it sloshes on land, some of it turns, but just like the bathtub, all right, if you scoop out a bunch of water or you move the water in a different direction, it bumps into something and goes off. Water has to come in from somewhere to take its place, and that's oftentimes from below. So we have mixing of the ocean in the vertical, not just in the horizontal. And this is basically two ways, upwelling and downwelling. So if you think about the wind flow here in this schematic coming, in this case, let's call it southward toward you, if you will, but southward, the continent there on the right side of that image, open ocean on the left side of that image. The wind is blowing south. That Ekman transport is perpendicular. The net transport, again, the surface is 45 degrees from that, but the net, when you go through the whole depth of the atmosphere, that whole, depth of the ocean, right? The net motion is going to be 90 degrees to the right. And I say to the right with respect to the direction that the wind is flowing. All right, so that water is moving to the left in this particular image. Again, it's to the right with respect to the wind direction, but looking at this image, it's to the left and away from the continent. So if that water is being effectively moved away from the continent, there's going to have to be some water coming in to take its place. And part of that is going to be coming from below. And it kind of makes sense that if you have water that's a lot deeper and that is not closer to the surface where the sun is hitting it, that water down here is going to be a lot colder than the water up here. So as you whisk this water away, the water comes up from below to take its place. So it's upwelling, thus the name. So the surface waters are being replaced by water that is welling up from below. Right? Not surprisingly, it works the other way around. All right, in this case, the wind is blowing to the north, so there's a net transport toward the coastline. So water is starting to pile up. So there's actually a little net sinking or a downwelling. So it works both ways. And these are part of the ways that we get ocean currents, winds driving ocean currents, and that type of thing. So when we think about things like, let's think about the Pacific Ocean, because we're going to talk more about that in a minute. Think about the North Pacific Ocean, again, from the equator northward up to the Gulf of Alaska. That's a big gyre in a clockwise direction, bringing cool air, all habits die hard, cool water down from the subarctic, if you will, down the coast of California. All right, so what we end up seeing is upwelling, most common along the west coast of continents. So upwelling and downwelling are occurring in the open ocean, in addition to next to continents, where wind patterns are converging. Think about the trade winds. Think about stuff that is right along the equator, where we know trade winds, those winds that are converging near the equator. In the northern hemisphere, they're coming from the northeast. From the southern hemisphere, they're coming from the southeast, and they're converging along the equator. Remember the intertropical convergence zone, where the air is converging in the tropics, in that zone where we get that ribbon of convection and thunderstorms. So it kind of looks like this. This one's a little bit complicated, so let's walk through it. The bottom of that, you'll go from 5 degrees north latitude to 0 degrees to 5 degrees south. Okay, so that's the ocean. Then that top part shows you what the wind vectors are. So again, the left half of that, you've got winds that are coming from the northeast and then from the southeast on the other side. All right, so northern hemisphere is there on the left. So if you're thinking and look at that way is north, and that way is south. So you've got winds from the northeast, winds from the southeast converging near the equator. All right, but the transport of the water, the net transport of the water's not smashing into each other. The water's actually being pulled away because of the Ekman transport. The Ekman, sometimes it gets called Ekman pumping. I prefer the term Ekman transport. It's being pulled away. So as a result, sometimes the water right on the equator is locally cooler than the water just a few degrees away from the equator. And that's what the bottom part of that graphic is showing. You've got the cold subsurface water, which upwells near the equator. And you've got warmer water on either immediate side. Thermocline is that area where there's not much of a change in water temperature. It's much more well mixed in the top level of the water. Then once you get below the thermocline, that's where the water is just cold all the time. So you take all of that stuff together, everything I just said, and remember that, okay, well, we've got rotating planet, we got winds blowing, we got oceans current, we got running into continents, we got winds bumping into each other, and this was discovered in the 20th century. There is a massive circulation of water that covers effectively the whole globe. It's called the thermohaline circulation. Thermo meaning temperature, haline for salt. So that's a temperature salt circulation. It's a very deep ocean circulation driven by variations in the density. Remember, to get the density of the water, you've got to think about the temperature and the salinity. Because salty water is a lot denser than fresh water. All right, so cold, salty water is going to be way, way more dense than warm, fresh water. All right, so once you run all these things together, you get this mess. All right, but this is the idealized thermohaline circulation, or sometimes called the Grand Ocean Conveyor Belt. That's a big fancy term for this. But for this part, focus on North America right now. And the orange line there, which is basically indicating where the Gulf Stream current is, what we're most interested in here in the eastern United States, eastern North America. That water goes up to the North Atlantic, it cools, it gets salty, and then it sinks. And then it actually goes back down to the south, closer toward the ocean floor, to the South Atlantic, gets all the way down to Antarctica, again, to the Ekman pumping and the rotation of the Earth and all that, it begins to rise again in the Indian Ocean, right? And you've got other subcurrents that also result. You know, you've got one branch, the deep cold current, sometimes called the circumantarctic current. I mean, basically, it goes all the way around Antarctica. It's a cold current that goes all the way around Antarctica. But it also comes back north through the Pacific, where it begins to warm back up. And then heads back across the Indian Ocean into the South Atlantic, higher up. All right? But again, for our purposes, the most important thing to know is that the Gulf Stream is part of the thermohaline circulation. Don't fret too much about knowing which way this thing is moving in the Indian Ocean. It's not that important. The important thing to notice is that the ocean is connected and it is moving up, it is moving down. It is always in motion. There is always a transfer of heat energy. It isn't just the Pacific stays there all the time. The Atlantic stays there all the time. The ocean moves and it transports energy. And this brings us to the most important part of this lecture. We know, okay, we've got ocean currents moving, we've got ups and downs, it's all bumping into each other. How does that ultimately affect climate? The biggest climate driver that is the interaction between the ocean and the atmosphere is this, the El Niño Southern Oscillation. You've probably heard of the El Niño. Back in my day, as they say, the El Niño really wasn't public knowledge. Nowadays it is, but it is part of a greater circulation called the El Niño Southern Oscillation. So what is this? Let's start with the Southern Oscillation. The El Niño is the water part. The Southern Oscillation is the atmosphere part. The Southern Oscillation is this kind of seesaw variation in the air pressure in the tropical South Pacific and Indian Oceans. Right? It's an examination of the mean atmospheric pressure in Darwin, Australia, and Tahiti. All right, so we look at that fluctuation in air pressure, and that's the Southern Oscillation. Do know that, please. The Southern Oscillation by itself is an air pressure oscillation. Tahiti minus Darwin. By convention, it's Tahiti minus Darwin. All right. The oceanographic effect from that is the El Nino or La Nina. But these things are intrinsically tied. That's why you will often hear it called ENSO, El Nino Southern Oscillation. Even though you hear less and less about the Southern Oscillation nowadays, and it's all about ENSO, or excuse me, it's all about El Nino. Old habits die hard. But the Southern Oscillation is the pressure oscillation. So what does that look like? So here's a schematic. Top graph, what we're looking at is basically the Pacific Ocean along the equator. To the right side, you can see South America and Mexico, Central America. Left side, you can make out Indonesia, Australia, and Southeast Asia. All right, so big L on the top graphic, Tahiti. Big H on the top graphic, near Darwin, Australia. I mean, Darwin's a little bit farther south, but for our purposes, this is pretty close. All right, so in an El Nino situation, the southern oscillation is negative. You've got relatively low pressure near Tahiti, relatively high pressure in Darwin. You do the math, your southern oscillation is going to be negative. All right, this is tied to the El Nino. And then the reverse is true. When the air pressure is higher in Tahiti than in Darwin, your southern oscillation is positive. And that's a La Nina. Okay, so what are the La Nina and the El Nino? The El Nino is the warm water phase of this thing, if you will. It's warm water episodes accompanied by significant changes in the sea surface temperatures over vast areas of the tropical Pacific, meaning that's going to lead to major shifts in atmospheric and oceanic circulations. All right? There is a lot of energy in the ocean because, as we know, it takes a lot of energy to change the temperature of water, either up or down. And the Pacific is huge. It's the biggest ocean basin we've got. And so you're at the equator, where you've got so much incoming solar. So you've got a massive storehouse of energy near the equator. So when you just nudge that one direction or the other, it has a fundamental change in that atmospheric sea interaction. And that's what will cause a lot of changes in the climate pattern downstream. It is not a very regular occurrence. The El Nino tends to happen every 3 to 7 years. It'll last about a year and a half, but it's not regular. One of the things that's not understood very well is the periodicity of this. The scientific community is getting better at forecasting it, but it's not great. There's some skill, but you can't go to the bank with it just yet. All right, so what does the El Nino look like? And I grabbed these images from the Australian Bureau of Meteorology, and there's a couple of video links that you really ought to watch because they're really, really good. All right, so when we look at the El Nino, this is when the regular trade winds, remember I said that the trade winds are converging near the equator. You've got winds from the northeast and from the southeast bumping each other, the equator, and then running off toward the western Pacific, Indonesia, Southeast Asia, Australia. Okay? When those winds weaken, all right, because you've got a change in the pressure, going back to the southern oscillation, right? The southern oscillation is negative. There is not as much of that trade wind blowing back up toward the western Pacific. So as a result, you tend to have a little more warm water, not upwelling. You've lost your upwelling along the coast of South America. So your water there is a lot warmer than normal. All right, so your trade winds, not as strong. You're not getting upwelling of cold water off the coast of South America. And this is going to fundamentally change weather patterns. La Nina is the opposite. You can think of La Nina as kind of an intensification of normal. This is when the trade winds are unusually strong, and that means the upwelling that normally happens there off the coast of South America is stronger. And then that looks more like this. All right. That's an intensification of the normal state of the atmosphere ocean. All right, so you've got a lot stronger trade winds along the equator, again, from east to west. So now you've got much warmer water really focused in on Indonesia, northern Australia. All right, and you've got much cooler water from the central part of the Pacific near the equator all the way back toward the coast of South America. Right? And because this is such a massive storehouse of energy, that feeds back into the atmosphere, what we call Rossby waves. It changes how energetic storms can be, especially during the winter months. The effects of an El Nino or La Nina are most pronounced in the winter. Why? Because we don't have as much sun. Sun is driving more weather in the summer. When the sun is not as strong in the winter, we're looking at other things to drive the climate. And this is one of them. This is a time series of what's called the historical Niño 3.4 area. It's a section of the equatorial Pacific, not the entire basin, but there's just one section. It's about 100. It's from like 180 degrees longitude to about 150 degrees west longitude along the equator. The point being here is that you see these ups and downs since 1982. These are correlating to periods that are El Niños versus periods that are La Niñas. All right, those big spikes are very strong El Niños. Those drops are strong La Niñas. You might have heard a few years ago we had a massive El Nino in 1516. That's what you see the big spike there toward the far right part of the screen, where the temperature was about 2 to 3 degrees Celsius above the long-term average. So that's more like 2 to 3 C. That's more like 3 to 5 Fahrenheit, which is pretty warm. Think about how much energy it takes to raise water a degree Fahrenheit, and then think about how massive the Pacific Ocean is. You're talking a lot of big change in energy. The climate impacts, don't commit this to memory, but you should know at least this part in North America, that again, we talk about the impacts of El Nino or La Nina. They're most felt during the local winter. And when I say local winter, remember that winter in the southern hemisphere is June, July, and August. Winter in northern hemisphere is December, January, and February. That's why you see the two changes there. We don't have as much of an impact in the summertime in the U.S., in the northern hemisphere. That's why it looks a lot quieter there in the northern hemisphere, June, July, August. So for our winter, an El Nino tends to make the southern tier United States cooler and wetter because you've got a much more active subtropical jet stream. You've added more moisture into the system because you've added more heat into the system down near the central and eastern Pacific. That gives you a more energetic subtropical jet stream. Not the Arctic jet stream, but the subtropical jet stream. So you tend to have more energetic storms coming into California and ultimately across the southern tier United States. So it's not cold in the southern U.S., but it's cooler than the long-term average. But also because of that, it tends to be milder and drier in western North America and the Gulf of Alaska because there's been a fundamental shift in the primary storm track. So don't get me wrong, it's not going to be hot in Juneau, Alaska, or Kamloops, British Columbia, but it will be milder and drier than an average or typical winter. La Nina, as you might guess, flips it. So it is cooler and it is wetter because you've got a primary storm track a lot farther to the north in coastal Alaska and into British Columbia and the Pacific Northwest, and ends up being drier and milder across the southeastern United States. In Virginia itself, the impacts aren't quite as strong, but we do see it a little bit. And it's also important to know that not every El Nino is created equally. There are other background things going on. You'll hear things tossed around like the Indian Ocean Dipole. You hear about the North Atlantic Oscillation. All these other things are very important as well. But when we try to tease out specifically the El Nino, these are where some of the climate impacts are. Again, these are relative to the long-term normal. There are a couple of videos. Please watch these. They're not long. The Australian Bureau of Meteorology does a very good 4 or 5 minute video about El Nino Southern Oscillation. Animates. It's gorgeous. If you're looking for something a little more off kilter but fun, there's another one from the PBS Digital Studios that talks about it the same way, where it uses a bathtub analogy. That's also worth the 7 or 8 minutes, and talks a little bit about chaos theory as well. So please take a look at those 2 videos. Of everything through the lecture today, it is fundamental that you understand the basics of the El Nino Southern Oscillation, because it is the main ocean atmospheric driver of long-term climate patterns, or short-term climate patterns, excuse me. I have to be careful with short and long-term. It drives a lot of variability, a lot of short-term variability. It doesn't affect the longer-term climate patterns, but it does affect the short-term variability. Why are some seasons wetter? Why are some seasons drier? Why are some seasons cooler? Why are some seasons hotter? That kind of thing. And that's it for this week. Again, El Nino, Southern Oscillation, good stuff. And understand ocean currents, that we have ocean currents. That's a very big deal also. Next time, we'll talk about paleoclimates, how we know what the climate was like 500, 1,000, 5,000, 25,000, 100,000 years ago. We have to use proxies to make these determinations, since we didn't have a lot of people taking notes back then. Before the next lecture, please take a moment and watch that video from PBS Nova, Decoding the Weather Machine. That's all about paleoclimates. It is longer, no questions longer. Break it up into 2 or 3 sections if you want, with a cup of coffee or a bowl of noodles or whatever. But there's very good stuff in there to tell you how we know what happened a long time ago.